the quantum whisper, unveiling the universe's hidden heartbeat for countless ages. Humanity gazed upon the night sky, enchanted by the stars, yet mystified by the seemingly empty space between them. Our ancestors, and even brilliant minds like Isaac Newton, pictured this space as a vast, unchanging stage, a void, a blank canvas upon which the cosmic drama of planets and galaxies unfolded. It was perceived as fundamentally passive, a mere backdrop to the vibrant dance of matter and energy. But then the early 20th century dawned, bringing with it a revolution in how we understood the very smallest things in existence: quantum mechanics. This new science wasn't just about tiny particles. It forced us to rethink the nature of reality itself, especially that supposedly empty space. What we discovered was mind-boggling. Far from being a desolate void, this emptiness was a teeming, frothing, incredibly active place. We now call it the quantum vacuum, the illusion of emptiness, more alive than you think. Imagine the calmest desert you can picture, silent and still under the vast sky. Now imagine if, underneath that seemingly inert surface, there were rivers flowing, volcanoes bubbling, and countless living creatures burrowing and stirring. That's a closer picture of the quantum vacuum. It appears empty, but it's actually the universe's most fundamental, energetic, and restless foundation. At the heart of this activity lies one of the most profound principles in all of science: Heisenberg's uncertainty principle. It's a fundamental property of the universe. This principle tells us that we can't simultaneously know certain pairs of things about a tiny particle with perfect precision. More crucially for our story, it also says you can't know a particle's energy and the time it exists with perfect certainty at the same moment. What does this mean for empty space? But that would defy the uncertainty principle. To satisfy this fundamental rule, the energy in any given region of space must fluctuate. It simply cannot stay perfectly still. These unavoidable, inherent fluctuations manifest as the spontaneous, transient appearance and disappearance of virtual particles. Think of them as incredibly short. They pop into existence for an infinitesimally brief moment, borrowing energy from the vacuum, and then almost immediately annihilate each other, paying back the borrowed energy. This happens continuously, everywhere, all the time. They are so fleeting that we can't directly see them in isolation, but their collective presence and interactions are very real and have measurable effects. The universe, woven from fields, the fabric of reality. To understand virtual particles even better, we need to think beyond individual particles and embrace the concept of quantum fields. In modern physics, we don't really see the universe as being made of tiny, solid billiard balls called particles. Instead, the universe is built from fundamental fields that permeate all of space. There's an electron field, a photon field for light, a quark field, and the famous Higgs field. Imagine a vast, perfectly still pond. If you drop a pebble in, you create a ripple. That ripple is like a particle. The pond itself is the field. Even when there are no real ripples, particles visible, the pond field is still there. The quantum vacuum is essentially the lowest possible energy state of all these fundamental fields combined. It's not truly empty because these fields are always present. And because of the uncertainty principle, they're always vibrating, always fluctuating, even at their lowest energy level. So, the quantum vacuum is this bubbling, frothing, energetic sea of potential, constantly teeming with these fleeting virtual particles. It's the dynamic substratum of reality, tangible proof. The Casimir effect and Lamb shift, this idea of a lively vacuum, isn't just a wild theory. It's backed by experimental evidence. The most famous example is the Casimir effect, which we touched upon earlier. Let's delve into its beauty. Imagine two perfectly flat, uncharged metal plates placed incredibly close together in a vacuum, perhaps just a few nanometers apart. Outside the plates, virtual particles of all possible wavelengths can spontaneously appear and disappear. But between the plates, only virtual particles with wavelengths that precisely fit into that tiny gap can exist. This is like only allowing certain sized waves to form in a very narrow channel because there are fewer possible modes or wavelengths of virtual particles allowed between the plates than outside them. There's a slight imbalance. It creates a tiny but measurable net attractive force that pushes the plates together. It's as if the quantum pressure from the vacuum is greater outside the plates than inside, squeezing them together. This minute force, first predicted in 1948 and later measured with remarkable precision, provides stunning experimental confirmation that the quantum vacuum is not inert. It possesses real physical properties and energy. Another piece of evidence is the Lamb shift, observed in atomic physics. Electrons orbiting an atomic nucleus are predicted to have specific energy levels. However, experiments showed slight deviations from these predictions. This discrepancy was explained by the interaction of the electron with the virtual particles constantly popping in and out of existence in the vacuum surrounding it. These tiny, fleeting interactions subtly shift the electron's energy levels, a phenomenon that has been precisely calculated and confirmed, further solidifying the active nature of the quantum vacuum. The vacuum catastrophe, a grand puzzle, however. This lively vacuum also presents one of the deepest and most perplexing problems in all of physics, the cosmological constant problem, often called the vacuum catastrophe. Remember that zero-point energy we talked about, the irreducible energy, even at absolute zero. When physicists try to calculate the total energy density of the quantum vacuum by summing up the zero-point energies of all known quantum fields, the answer is colossal. It's an astronomical number, many orders of magnitude, something like 10,120 times larger than the actual tiny amount of vacuum energy we observe in the universe today, which we call dark energy. If the vacuum truly had this much energy, it would be so incredibly dense and powerful that its gravitational influence would be overwhelming. The universe would have expanded so violently and rapidly that it would have torn itself apart almost instantly after the Big Bang. Stars, galaxies, atoms, and certainly life would never have had a chance to form. The very fact that you and I are here observing the universe means that most of this predicted vacuum energy must somehow cancel out to an almost absurd degree of precision. Why this happens is one of the biggest unsolved mysteries, a major hint that our current theories of physics are incomplete. This fine-tuning points to either a deeper underlying principle, a specific mechanism we don't understand, or a selection effect in a vast multiverse. The cosmic spark, how our universe took its first breath now that we understand the vibrant nature of the quantum vacuum. let's return to the most dramatic moment in our story, the very first breath of our universe, driven by a phenomenon called cosmic inflation. This isn't just a theory about how the universe expanded. It's a story of how an infinitely tiny seed blossomed into the vast cosmos we inhabit, the unstable seed, the false vacuum, and the inflattened field. Imagine our universe before it was everything. It wasn't a dense fireball yet. Instead, it was likely an incredibly tiny speck, perhaps far smaller than a single atom. This speck wasn't just nothing, but rather a region of the quantum vacuum, stuck in a highly unstable, high-energy state, a false vacuum. Think of a ball sitting on a plateau at the top of a very steep, very high hill. It's momentarily stable, but it's holding an enormous amount of stored-up potential energy. This potential energy is associated with a hypothetical field called the inflattened field. Just as the Higgs field gives particles mass by its pervasive presence, the inflated field is theorized to have filled this tiny, early universe. In its high-energy, false vacuum state, its potential energy was colossal. What caused the ball to roll? A random, tiny quantum fluctuation. Just one of those inevitable jitters in the quantum vacuum, a microscopic ripple, was enough to push the inflattened field off its unstable plateau. Like a dam breaking, this triggered a phase transition. The inflattened field began to roll down its energy landscape to a lower, more stable energy state, a true vacuum. As it rolled, it unleashed its immense, stored potential energy. The exponential stretch, inflation's incredible power, the release of this energy didn't cause an explosion into existing space. Instead, it caused space itself to stretch exponentially. This is the core of cosmic inflation. During this unbelievably rapid phase, which lasted for a mere fraction of a second, something like 1036 to 1032 seconds after its onset, the universe expanded at an accelerating rate that makes anything we observe today look sluggish. In that blink of an eye, a region smaller than an atom could have ballooned out to be larger than a grapefruit, or even many light years across. How did this work? The inflattened field, while slowly rolling down its energy hill, acted like a kind of negative pressure. In general relativity, negative pressure causes accelerated expansion. It's a bit counterintuitive, but think of it like this. Normally, gravity pulls things together, but this inflattened field's immense potential energy was so dominant that it created a powerful, repulsive anti-gravity force, literally stretching the fabric of space-time outwards at an astonishing speed. Reheating. The birth of the hot Big Bang inflation didn't last forever. Eventually, the inflattened field reached the bottom of its energy valley. At this point, it rapidly oscillated like a bouncing ball, losing energy at the bottom of a bowl. As it oscillated, its energy decayed and transferred into a searing hot, dense soup of all the known elementary particles, quarks, electrons, neutrinos, photons, and so on. This process is called reheating, and it marks the true beginning of the hot, dense Big Bang phase that our standard cosmological models describe. All the matter and energy we see in the universe today are ultimately the descendants of this initial burst of energy from the decaying inflattened field. Inflation's elegant solutions, the mysteries unraveled. One of the most compelling reasons scientists embrace inflation is its ability to elegantly solve several puzzles that the standard Big Bang model without inflation struggled to explain the horizon problem, the universe's uniformity. Look at the cosmic microwave background, CMB, the faint glow left over from the Big Bang, like an ancient baby picture of the universe. It shows that regions of the universe that are so far apart, they couldn't possibly have interacted with each other. Even if signals traveled at the speed of light, since the Big Bang have almost exactly the same temperature. How did they achieve such a uniform temperature if they were never in contact? Inflation provides the brilliant answer. Before inflation, all these regions were incredibly close together, small enough to have interacted and reached a uniform temperature. Inflation then stretched them apart, making them appear far away today. They were in causal contact before inflation, the flatness problem, the universe's balance. Our universe appears remarkably flat, meaning its geometry is very close to Euclidean, like a flat sheet of paper, where parallel lines never converge or diverge. This is a delicate balance. If the universe's initial energy density was even slightly above or below a critical value, it would have quickly curved up like a sphere if too dense, or opened up like a saddle if too sparse. Inflation solves this by taking any initial curvature, no matter how extreme, and stretching it out until it appears flat. Just like inflating a crumpled balloon makes its surface look smooth from a distance. The monopole problem. Missing magnetic poles. Some advanced particle theories predicted that the incredibly hot, dense early universe should have produced vast numbers of magnetic monopoles, isolated north or south magnetic poles. Unlike the magnets we know, which always have two poles, we've never observed any. Inflation solves this by simply diluting them to such an extent that their density in our observable universe becomes effectively zero. They're still out there, just too far apart to ever find the origin of structure. Seeds of galaxies, perhaps the most beautiful solution provided by inflation, is how it explains the origins of all the large-scale structures we see today. The vast cosmic web of galaxies, clusters, and superclusters. Remember those tiny, unavoidable quantum fluctuations in the vacuum, the very ones that might have triggered inflation. As inflation violently stretched space, these microscopic ripples were stretched to becoming macroscopic. These tiny variations in energy density became slightly overdense and underdense regions. Over billions of years, gravity then relentlessly pulled more matter into the slightly overdense regions, acting like a cosmic sculptor, forming the vast structures we observe. So, the entire cosmic architecture, from the smallest star to the largest galaxy cluster, ultimately traces its lineage back to those fundamental quantum jitters in the incredibly early universe. The hunt for inflation's signature, primordial gravitational waves. Inflation makes a bold and testable prediction that physicists are desperately searching for. Primordial gravitational waves, the violent, accelerated stretching of spacetime during inflation should have generated ripples in spacetime itself. These gravitational waves are different from the ones detected by instruments like LIGO, which come from crashing black holes or neutron stars. These are cosmic echoes from the very dawn of time. These primordial gravitational waves would leave a unique swirling pattern of polarization in the cosmic microwave background, CMB, known as B modes. Think of the CMB as light that has traveled across the entire universe, carrying imprints of its early history. Detecting these B modes would be like finding the specific fingerprints of inflation, almost a smoking gun for its occurrence. Current observational efforts, like the BICE-P Keck array, and future missions, like Light Bayard and CMBs-4, are dedicated to finding this incredibly faint signal. While some early claims turned out to be from galactic dust, the search continues with increasing precision. A definitive detection of primordial B modes would be one of the most significant breakthroughs in cosmology, solidifying in place as a fundamental part of our universe's origin story. Beyond our beginning, tracing the cosmic lineage, the Big Bang, with inflation, tells us a spectacular story about our universe's beginning. But what if it wasn't the absolute beginning? What if it's just one incredibly dramatic chapter in a much, much longer, perhaps eternal, cosmic saga? This is where the story truly ventures into the realm of the mind-bending. Scientists are exploring fascinating ideas that suggest our universe might have a deeper cosmic lineage, a history that stretches beyond our Big Bang, the endless dance. Cyclic universe models imagine the universe not as a one-time event, but as a repeating cosmic dance of birth, death, and rebirth. This is the essence of cyclic universe models, the big crunch and the big bounce in some versions. Our universe expands, but gravity eventually wins. The expansion slows, then reverses, and everything starts collapsing back together into an incredibly hot, dense state, the big crunch. But instead of collapsing to an infinite, problematic point, a singularity, something incredible happens. As the universe reaches extreme density, the very rules of quantum gravity kick in, preventing total collapse. Instead, a powerful, repulsive force emerges, causing the universe to bounce back out into a new expansion, creating a fresh Big Bang. Our universe, then, would be just one cycle in an infinite series of these cosmic breaths. This is particularly explored within loop quantum cosmology, LQC. In LQC, the fundamental nature of space itself, being made of tiny, indivisible pixels, means that density can never truly become infinite. There's a maximum density, the Planck density, unimaginably vast, that acts as a cosmic bouncer, preventing singularity and ensuring the rebound. But a quantum bridge, connecting a contracting past to an expanding future. Memory of the past. A fascinating implication of the Big Bounce is that each new universe might carry subtle memories or imprints from the previous cycle. For instance, tiny differences or patterns in the cosmic microwave background, CMB, that don't quite fit the standard inflationary model might be echoes from the universe that existed before our Big Bounce. This is an active area of theoretical and observational search. Challenges for cyclic models, the entropy problem. One of the biggest difficulties for many cyclic models is the entropy problem. Entropy is a measure of disorder, and the laws of physics state that the total entropy of the universe always increases. If each cycle adds entropy, then successive cycles should get longer, larger, and progressively more diluted or disordered. Eventually, low entropy, Big Bang. To overcome this, cyclic models need clever mechanisms to either reset entropy between cycles or to bypass this problem entirely, as some advanced models try to do. The infinite forest, the multiverse explored. The idea of the multiverse takes our story beyond a single universe placing it within an infinitely grander cosmic tapestry. It's not just one theory, but a collection of ideas: eternal inflation and the fractal multiverse. This is one of the most prominent ways the multiverse arises. In this picture, inflation, once it starts, never truly stops everywhere. Imagine a vast, ever-expanding foam. In some regions, inflation continues accelerating space endlessly. But in other pockets, inflation turns off, and these pockets detach, forming bubble universes like our own. Our universe is simply one such bubble. This process is eternal in the future. New bubble universes are constantly being born. The resulting structure is often described as a fractal multiverse, infinitely complex and self-similar, with universes possibly nesting within other universes or branching off in an endless array. Varying physical laws, the landscape. A key feature of the multiverse from eternal inflation is that each bubble universe can have different physical laws and fundamental constants. When the inflattened field rolls down its energy hill, it might fall into different valleys on a vast inflattened landscape, each corresponding to a different set of universal parameters. This means some universes might have stronger gravity, different types of particles, or even different numbers of spatial dimensions. The anthropic principle. This helps address the fine-tuning problem, why our universe's constants seem so perfectly set for life to exist. In a multiverse, it's not that our universe is special or finely tuned by design. It's simply that we can only exist in the universes where conditions allow for life. We naturally find ourselves in one of the lucky bubbles. It's like finding yourself on an Earth-like planet in an infinite cosmos. It doesn't mean the cosmos was designed for Earth, just that you couldn't be anywhere else. Brain, cosmology, and colliding worlds, from advanced theories like string theory or its overarching framework, M-theory, flexible sheet, or brain floating within a larger, hidden, higher dimensional space called the bulk. This bulk could have many more dimensions than the three we experience. The cosmic collision. Our Big Bang wasn't a singularity. Instead, it was caused by a colossal head-on collision between our brain and another parallel brain in the bulk. Imagine two enormous, invisible sheets in a higher dimension slamming into each other. The immense energy released from this collision would manifest in our 3D brain as the hot, dense, rapidly expanding state we call the Big Bang. Cyclic brain worlds. This model can naturally lead to a cyclic universe. After the collision, the brains might recoil from each other, drift apart, and then be slowly pulled back together by a force in the bulk, leading to another collision and another Big Bang, creating an endless loop of cosmic creation. This offers a compelling alternative to both the singularity of the Big Bang and the Big Bounce by suggesting a cyclical process driven by interactions in higher dimensions. The many worlds interpretation of quantum mechanics Level 3 multiverse. This is one of the most mind-bending ideas, directly from the heart of quantum mechanics. It suggests that every time a quantum event happens, like an electron choosing to be in one state or another, or a photon hitting a detector, the universe doesn't just resolve into one outcome. Instead, it splits into multiple parallel universes, each representing a different possible outcome. This means there's a universe where you chose coffee, and another where you chose tea, a universe where you took that job, and one where you didn't. An uncountable number of parallel realities are constantly branching off, creating every single possible version of events from every quantum interaction. It implies an endlessly branching reality where all possibilities are realized. The parent universe and cosmic natural selections. Some of these multiverse ideas lead to even deeper, more philosophical concepts: black hole universes and cosmic fecundity. What if our universe literally grew inside a black hole within a parent universe? This intriguing idea, explored in some quantum gravity theories, suggests that the incredibly dense core of a collapsing star, which normally forms a black hole, doesn't become a singularity. Instead, quantum effects cause it to bounce and expand, forming a new, entirely separate universe within the event horizon. Our Big Bang would then be the birth of our universe from such an event. This would mean matter is never truly destroyed, just recycled into new cosmic containers. Lee Smolin's cosmological natural selection. This bold theory, related to the black hole universe idea, proposes a kind of evolution in the multiverse. Universes that produce more black holes are more fit for reproduction because each black hole is a potential parent to a new universe. This means the fundamental constants and laws of physics that lead to abundant black hole formation, and therefore abundant stars and galaxies, would be naturally selected and passed on to subsequent generations of universes. Our universe, rich in black holes, might simply be a successful progenitor in this cosmic evolutionary process. The unified code weaving gravity into the quantum fabric to truly unlock the secrets of the very first moments of existence. We need a complete code or rulebook for the universe. Right now, our cosmic library has two separate, incredibly powerful but ultimately incompatible volumes: Albert Einstein's general relativity, GR, and quantum mechanics, QM, general relativity, GR, the grand architect of the cosmos. Einstein's GR revolutionized our understanding of gravity. It showed us that gravity isn't just a force pulling objects together, but rather a manifestation of the curvature or warping of space-time itself caused by mass and energy. Imagine a bowling ball, a massive object placed on a stretched rubber sheet space-time. The ball creates a dip, and marbles rolling nearby will curve towards the bowling ball, not because it's pulling them directly, but because they're following the curve in the sheet. GR describes the elegance of black holes, the expansion of the universe, and the ripples of gravitational waves. It works beautifully on cosmic scales. Quantum mechanics, QM, the strange world of the very small, QM, on the other hand, rules the incredibly tiny world of atoms, particles, and fundamental forces: electromagnetism, the strong force, the weak force. It's a world of probabilities, uncertainties, and bizarre phenomena, where particles can be in multiple places at once or instantly influence each other across vast distances. Entanglement. QM underlies all of chemistry, biology, and the technology we use every day. It works flawlessly at microscopic scales. The cosmic collision, where theories break down the critical problem, is that at the Planck scale, the unbelievably tiny and energetic conditions of the very early universe and inside black holes, both GR and QM become relevant, but they give conflicting answers. Imagine trying to describe a calm ocean using only rules for individual water molecules, and then trying to describe the individual water molecules using only rules for ocean currents. It wouldn't work. At the Big Bang, the entire observable universe was squashed into a volume smaller than a single atom, reaching unimaginable densities and temperatures, the Planck epoch. Here, gravity was as strong as the other quantum forces. But GR predicts an infinitely dense point, a singularity, where all its equations break down. QM, which doesn't include gravity, is also incomplete. This collision of theories is the biggest unresolved problem in physics. The search for quantum gravity is the quest to find a single, unified theory that merges GR and QM, creating a consistent framework that works at all scales, from the smallest quantum fluctuations to the largest cosmic structures. This is the holy grail of physics, leading candidates for quantum gravity. New rulebooks for reality. The scientific community has put forward several ambitious proposals for this unified rulebook: string theory and M theory. The universe as vibrating strings beyond point particles. String theory is arguably the most ambitious candidate for a theory of everything. Its core idea is revolutionary. What if the fundamental building blocks of the universe aren't tiny, dimensionless, point-like particles, but rather incredibly tiny, one-dimensional, vibrating strings? These strings are so minuscule, perhaps 10-35 meters long, the Planck length, that even with our most powerful microscopes, they would appear as points, different vibrations, different particles. The genius of string theory is that different modes of vibration of these fundamental strings correspond to different particles. One vibration pattern might be an electron, another a photon light particle, another a quark. Crucially, one of these vibration patterns corresponds to the graviton, a hypothetical massless particle with spin 2, which is theorized to be the quantum carrier of the gravitational force. This is why string theory naturally incorporates gravity and is a leading candidate for quantum gravity. Supersymmetry. For string theory's mathematics to be consistent, it requires a symmetry called supersymmetry. This means that for every known particle, like an electron or a photon, there should be a heavier superpartner. For example, the superpartner of an electron is a selectron, and for a photon, it's a photino. While we haven't found these superpartners yet, which is a challenge for string theory, they could explain the existence of dark matter and help unify the fundamental forces. Extra dimensions, compactification. Another striking prediction of string theory is the existence of extraspatial dimensions. While we experience 3 dimensions of space, length, width, height, and one of time, string theory typically requires 10 or 11 dimensions in M theory, an overarching framework that unifies different string theories. The reason we don't see these extra dimensions is that they are thought to be compactified or curled up into incredibly tiny, intricate shapes at every point in our familiar 3D space. Imagine a garden hose. From far away, it looks like a 1D line, but up close, you see it has a curled up 2D surface. The specific way these extra dimensions are curled up, compactification, determines the values of the fundamental constants like electron mass, strength of gravity, and the laws of physics we observe in our universe. This is how the string landscape arises, a vast number of ways to curl up the dimensions, each leading to a different universe. Loop, quantum gravity, LQG, the granular universe, quantizing spacetime itself. Unlike string theory, which aims to be a theory of everything, LQG focuses specifically on quantizing gravity and spacetime itself. It doesn't attempt to unify all forces, but rigorously quantizes Einstein's general relativity. No smooth fabric, but discrete pixels. LQG rejects the idea of spacetime as a smooth, continuous fabric. Instead, it proposes that space is made of tiny, indivisible, fundamental chunks, or quanta, like pixels on a screen. But in 3D, these are often visualized as tiny loops or nodes that are interwoven into a spin network. The connections in this network represent the fabric of space. The area and volume of space are also quantized, meaning they can only take on specific, discrete values, not continuous ones. There's a smallest possible pixel of area and volume, avoiding singularities and the big bounce, because space is granular. Matter can never collapse to infinite density. This is crucial for resolving the singularity problem. Instead of a singularity at the Big Bang or inside black holes, LQG predicts a bounce. When the universe contracts to the Planck density, the quantum repulsive forces of this granular spacetime become dominant, preventing collapse and causing a rebound into a new expansion. This is the big bounce. Background independence. A key strength of LQG is its background independence. It doesn't assume that space and time exist as a fixed stage before the theory starts. Instead, space and time emerge from the fundamental relationships and interactions of the quantum loops themselves. This is a very deep and attractive feature for a theory of quantum gravity. Causal set theory. Order from fundamental events, discrete events, not continuous spacetime. This theory is even more radical. It posits that spacetime is fundamentally discrete, made of individual, indivisible events, the only intrinsic property these events have is a causal order. One event can cause another. There's no inherent notion of distance, angle, or even dimensionality at the deepest level. These properties emerge statistically from the sheer number and arrangement of these causally connected events. Emergent geometry. The smooth, continuous spacetime we experience is an approximation that emerges from this underlying causal structure. The volume of a region, for example, is simply proportional to the number of causal set elements it contains. This approach naturally preserves Lorentz invariance, a fundamental symmetry of special relativity, even though spacetime is discrete. No singularities, again. Like LQG, causal set theory naturally avoids singularities because there's a smallest possible unit of volume, a single event, preventing infinite density. It inherently suggests a big bounce or some form of pre-Big Bang history. The emergence of reality, where space and time unfold. This is the most profound and perhaps most mind-bending part of our story. What if space and time, the very stage upon which the universe plays out, and the very flow that carries its story forward, are not fundamental ingredients of reality? What if they are, in fact, emergent properties of something even deeper and more abstract? Think of it like this. The sensation of temperature is very real to us, but temperature isn't a fundamental property of a single molecule. Temperature is an emergent property that arises from the average kinetic energy jiggling motion of countless molecules interacting. Zoom in on a single molecule, and the concept of temperature disappears. Similarly, some of the most cutting theories of quantum gravity suggest that space and time might be emergent properties. Zoom into the Planck scale, and the familiar notions of distance and duration might simply dissolve, giving way to a more fundamental, non-spatial, non-temporal reality. From information to geometry, the universe's secret code, one of the most compelling ideas in this realm is that information might be the most fundamental stuff of the universe, even more basic than matter or energy. The it from bit principle. The renowned physicist John Wheeler famously coined the phrase, it from bit, suggesting that every physical it, every particle, field, and even the fabric of spacetime itself ultimately derives its existence from bits of information. This isn't about the universe being a computer simulation, though some theories go there. It's about the deep idea that reality might be built upon fundamental units of information, the holographic principle and ADS-CFT. This is where it from bit becomes concrete. The holographic principle suggests that all the information contained within a volume of space can be encoded on its boundary, much like a 3D hologram is encoded on a 2D surface. The most striking realization of this is the ADS-CFT correspondence, anti-de Sitter, conformal field theory. It's a mathematically precise duality that shows that a theory of quantum gravity in a certain type of curved space-time anti-de Sitter space, which is like a box that keeps gravity confined, is exactly equivalent to a conventional quantum field theory without gravity, living on its lower dimensional boundary. This is revolutionary. It means that the geometric fabric of space-time gravity and even the existence of an extra dimension can emerge from the collective behavior and entanglement of fundamental quantum bits, the information on the boundary. It suggests that space-time isn't fundamental. It's a consequence of the way information is organized and entangled. Space-time from entanglement, EHR, building on the holographic principle. Some physicists propose an even deeper connection. Space-time itself is woven from quantum entanglement. This is famously captured by the conjecture equals EPR, proposed by Juan Maldacena and Leonard Susskind. EPR refers to the Einstein-Podolsky-Rosen paradox, which highlights quantum entanglement, the spooky action at a distance where two particles can be instantly linked, no matter how far apart they are. R refers to an Einstein-Rosen bridge, which is a type of wormhole, a theoretical tunnel through spacetime that connects to distant points. The EER conjecture suggests that these two seemingly disparate concepts are deeply linked. Highly entangled particles are, in a sense, connected by microscopic wormholes. More broadly, it implies that the very fabric of spacetime, its connectedness and geometry, arises from the entanglement of its underlying quantum degrees of freedom. If particles are entangled, spacetime is connected. If they become disentangled, spacetime might tear or break apart. This is a truly profound idea that could be a major key to unifying gravity and quantum mechanics. The mystery of time. Does it truly flow? If space emerges, what about time? Our everyday experience tells us time flows relentlessly forward, from past to future. But at the quantum level, things get much stranger. The problem of time in quantum gravity. In many formulations of quantum gravity, like LQG, time often disappears from the fundamental equations. The universe appears to be static or timeless. At the quantum level, this is because general relativity treats time as part of the dynamic fabric of space-time, while quantum mechanics typically assumes a fixed external clock. Reconciling these views is the problem of time, emergent time. This suggests that the flowing arrow of time we experience isn't fundamental, but also emergent. It might arise from the growth of entanglement as quantum systems in the universe become more and more entangled. They decohere, lose their quantum weirdness, and start behaving classically. And this process of increasing entanglement might be what gives rise to our perception of an irreversible flow of time. The cosmological arrow of time, the universe's relentless expansion. The cosmological arrow might be the fundamental driver for all other arrows of time, including the thermodynamic arrow, the increase of entropy or disorder. As the universe expands, it allows for more configurations, thus increasing its disorder. Discrete ticks. Some theories propose that time isn't a continuous flow, but a sequence of discrete ticks or events, like frames in a film at the Planck scale. Our smooth perception of time arises from many such ticks. A geometric, a temporal realm. If space and time are emergent, then the before the Big Bang isn't a when in a linear timeline. It's a fundamental state of reality prior to the emergence of time itself. Imagine a realm where there are no places or moments, only a network of fundamental relationships or quantum information. The Big Bang, then, is the grand phase transition where this abstract, non-spatial, non-temporal quantum realm crystallizes or unfolds into the dynamic, expanding cosmos with its familiar dimensions of space and its flowing arrow of time. It's not an explosion in time, but the very moment when time began to manifest. The ongoing saga, our quest for cosmic truth, our story of the universe's origin, is far from complete. It's an ongoing saga, driven by human curiosity and relentless scientific inquiry. Scientists across the globe, from the vast deserts of Baluchistan to the high-tech labs of Europe, are constantly pushing the boundaries of knowledge, seeking the faintest whispers of cosmic truth, hunting for the cosmic genesis. Observational frontiers. The challenge is immense. How do you test theories about conditions so extreme they existed before space and time as we know them, or at scales unimaginably smaller than anything we can probe directly? The answer lies in searching for incredibly subtle fingerprints left behind on the fabric of the universe. Reading the cosmic baby picture with new eyes, the cosmic microwave background, CMB. The CMB is literally the universe's oldest baby picture. A faint glow of light from when the universe was just 380,000 years old. It's a treasure map containing tiny temperature fluctuations that are the direct imprints of those primordial quantum seeds that were stretched by inflation. Polarization B modes, the holy grail. Beyond just temperature, the CMB also has a faint polarization, like light scattered off a surface. Scientists are desperately searching for a specific swirling pattern of this polarization, known as B modes. These B modes are considered the unique smoking gun of primordial gravitational waves, the ripples in space-time that would have been generated during the violent stretching of inflation. Detecting them would be monumental proof for inflation. While some initial claims were misleading, from galactic dust, dedicated experiments like Bicep Kekere in Antarctica, and next-generation observatories like Light by RD, a satellite mission by Japan, ESA, and CMBs for a massive, ground-based observatory in Chile and Antarctica, are pushing the boundaries of sensitivity. Non-Gaussianities, scientists also look for tiny deviations from perfect randomness in the CMB fluctuations, called non-Gaussianity. These can reveal details about the specific shape of the inflattened field's energy landscape, or even hint at interactions with other fields or branes from a multiverse. Anomalies and pre-Big Bang clues, some subtle anomalies in the CMB like an unexpected cold spot or alignments of patterns are vigorously debated. While most can be explained by standard physics, some researchers speculate they could be hints of physics from before our Big Bang, such as remnants from a previous cosmic cycle, as proposed by Roger Penrose's conformal cyclic cosmology, where concentric circular patterns in the CMB might be traces of gravitational waves from black hole collisions in a previous eon. Listening to the universe's deepest rumbles, next-gen gravitational wave detectors, current gravitational wave detectors, like LIGO and Virgo, have revolutionized astronomy by detecting violent events like black hole mergers. But these are relatively local events. The future promises much more sensitive instruments, future ground-based observatories, projects like the Einstein Telescope in Europe and Cosmic Explorer in the USA are planned kilometer-scale detectors that will be far more sensitive to gravitational waves, probing larger volumes of space, and potentially detecting fainter signals from the very early universe. Space-based observatories, LISA, the Laser Interferometer Space Antenna, LISA, a joint ESA-NASA mission, will be a colossal observatory in space, comprising 3 satellites forming a giant triangle millions of kilometers apart. LISA will be sensitive to much lower frequency gravitational waves than ground-based detectors, allowing it to hear different cosmic events, potentially including a primordial gravitational wave background, the continuous hum of gravitational waves generated during inflation or phase transitions in the early universe, providing a direct window into the Planck epoch. Black holes as cosmic laboratories. Black holes are where the mysteries of general relativity and quantum mechanics converge. They offer unique insights into quantum gravity. Black hole echoes. Some quantum gravity theories predict that gravitational wave signals from black hole mergers might have tiny, subtle echoes after the main signal fades. These echoes would be caused by quantum effects near the black hole's event horizon, where space-time might not be perfectly smooth, as GR predicts. Finding such echoes would be strong evidence for quantum gravity. Observing extreme gravity, directly observing the behavior of matter falling into black holes, or the very precise characteristics of the event horizons, could constrain or validate different quantum gravity models beyond colliders. Tabletop quantum gravity experiments. While we can't build a particle accelerator big enough to recreate Big Bang conditions, scientists are devising ingenious tabletop experiments to look for indirect signs of quantum gravity, gravity-induced entanglement, GE, a particularly exciting avenue, still mostly theoretical. but with early experimental attempts as of 2025, is to see if gravity can directly entangle to quantum systems. If we can put two tiny massive objects into quantum superposition existing in two places at once and show that their gravitational interaction alone causes them to become entangled, it would be powerful evidence that gravity itself has a quantum nature. This is incredibly difficult due to the weakness of gravity at small scales and the challenges of maintaining quantum coherence in larger objects. The endless question, why something, not nothing? Even if we perfectly describe how our universe emerged from a quantum vacuum driven by inflation, perhaps bouncing from a previous cycle, or being born from a higher dimensional collision, even if we find the ultimate theory of quantum gravity, a profound question will always remain. Why is there anything at all? Why these laws? Why this universe? The ground state problem revisited. Why does the quantum vacuum exist with its specific properties rather than absolute, featureless non-existence? Even the most fundamental theories require some underlying rules, some inherent potential for reality to unfold. What determined those initial rules? Mathematics as ultimate reality. Some philosophers and physicists, like Max Tegmark, propose the mathematical universe hypothesis, suggesting that every mathematically consistent structure is a universe. Our physical reality is simply one of these mathematical structures. In this view, existence is inherent in mathematics, and the universe just is a particular mathematical form. The universe as information. If the universe is fundamentally information, does that imply a programmer? Or is the information itself the ultimate irreducible reality? These are deeply philosophical questions. The quest for cosmic origins is a humbling yet exhilarating endeavor. It pushes us to the very limits of our imagination and intellect. It reminds us that our understanding of reality is always evolving, and the deeper we look into the nothingness, the more profound, intricate, and astonishing the story of everything becomes. It is a story that continues to unfold, one cosmic mystery at a time.